If you have ever wondered what tensors are, why they matter, and how they have shaped the way we understand the universe, you are in the right place. What exactly is a tensor? Is it just another mathematical concept, or does it hold the key to unlock the secrets of our world? Are tensors just an abstract concept for mathematicians, or do they have practical applications that can change the way we live, work, and explore the cosmos? Well, today in this exciting journey, we would be delving deep into the fascinating world of tensors. We are also going to dive deep into the fundamental concepts of tensors, exploring what they are, their intriguing history, and why they are an absolute must-know factor for everyone. We will also explore how these brilliant minds transform the world of mathematics and why tensors have become an essential tool in the field of physics, mathematics, as diverse as into engineering, machine learning, and even deep learning. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the very first lesson on tensor fundamentals, where I would be giving you a complete idea about what tensors are and in a very simple and easy manner. Before I go ahead and start this video, I would like to take a quick look back. And this look back is because it is not the first time that I'm making a video on tensors. Right on your screen, you can see these are some of the old videos which I made on vectors and tensors, including finding stress vector, backward transformation, vector components, etc. Now the question is that why again I'm making a fresh series of videos on tensors. The reason is that these are quite old, and if you look into the concept and the writing of tensors, it was around 2 years back, just when I started this channel Physics for Students. So I want to give a fresh look with a lot of new concepts added, with a lot of good animations, graphs, figures, mathematical concepts in a better way. But however, this is just a quick look back in case if you're interested to look into some of my old videos which are quite detailed in certain aspects. You can go into my playlist on tensors and you can look into it. However, this series would be much more detailed, much more clear, making a better understanding of tensors, on which I have already worked upon. So having looked into the nostalgic idea which I had done 2 years back, this is the right time now to look in what is a tensor. Let us look quickly into the next part of our video. As we all know that the origin of the words of physics or mathematics originates either from Latin or Greek, and tensor is also not an exception. It comes from the Latin word tender, it means to stretch, and in anatomy it calls a muscle that tightens or stretches a part of the body. That means it has something to do with stretching or pulling, or something I can say which stores information into some area which gets later stretched. Now here is a sphere, and I have stretched that sphere into what I called an oblate spheroid. Now what if I get an information over here, which is this red one, and when I put it on the oblate spheroid, which is a stretched part, it goes over here. So you see the information gets stretched out. So how will we come to know about the stretched information? Remember, the sphere was not a stretched one, but the information gets stretched into the oblate spheroid, which is a stretched part of the sphere. So as we start with the very word tensor, which means muscle which stretches or tightens, tensor actually we can tell is something which has to do with storing information which gets stretched over something, as we will later explore into manifolds and general relativity and Riemannian manifold. This is exactly the core idea which was further elucidated and expanded by mathematician and physicist. So for now on, what we know is that tensors are something which stores some amount of information which is a stretching information. On the right hand side, here is a more technical idea about what is a tensor: a set of components, functions of coordinates, any point in space that transform linearly between coordinate system. I have underlined the word linearly because that would carry a profound influence in our understanding of tensor. However, we will pause right now just to understand the definition as transform linearly between coordinate systems. So from here, two things become very clear. One is that there is a transformation between coordinate system and there is a linear transformation. What is that? What are the other things that helps into transformation. Let us look into the next part of our video. So on the left hand side, this is a schematic diagram of a tensor. Don't worry, we will expand on this. First, we would say that tensors are vectors and which have not a single direction but actually points in various other directions, which we will explore now. Tensors have both properties of vectors and scalars like area, stress, etc. We can also tell that tensor is obviously not a scalar and neither a vector, but mathematically we can tell it is an abstract quantity that obeys the coordinates transformation law. This is very central, and we are going to explore what do we mean by coordinate transformation law. Before that, let us look into another important feature, that tensors are geometrical objects that describe the linear relationships between geometric, numerical and other tensile vectors. So till now what we have understood is that this is a kind of a, we can say, an exotic mathematical concept, an abstract quantity which does not point in one direction just like vectors but in different directions, and it has got a linear relationship. So from here what we can deduce is that tensors are basically a kind of a generalization of scalars, vectors and matrices when it moves into higher dimension. What comes from here to be absolutely clear, crystal clear, would be that tensors actually hold data. So here is a schematic diagram of what we can call a data which is connected with various networks and nodal points, and we can say that number one, tensor is like a fixed flexible data structure. Obviously it can store numbers in grid of multiple dimensions, and that is why tensors are used in engineering and other level of physics and mathematics when we need to denote certain things which are not in 2, 3 or 4 dimensions. Third is that it organizes and manipulates data in a more complex way. Complex means it would be further complexities which arises due to storing of data, and tensors are mathematical abstract objects which are efficient enough to store complex data. So it is a kind of an arrangement of data which we are going to explore, but here comes a mathematical definition. A tensor is a mathematical object that describes a multilinear relationship between sets of algebraic objects related to a vector space. Tensors may map between different objects such as vectors, scalars, or even between tensors. We will look into the right hand side mathematical definition. What do we mean by vector space? What are multilinear relationship in due course of time? But this is an overall idea of what is a tensor. I know that things are not yet clear, but most important is that we understood these are flexible data structures storing data up to multi-dimension. But what actually makes tensors so important? What are the most striking important features of tensors which make them such beautiful objects? Let us look into the next part of our video. What are the important features of a tensor? I have taken this as a stress energy momentum tensor, which we will explore later. But the first thing is that remember that tensors can be of any rank. That means it can have n number of dimensions. We are going to explore mathematically into that. There is something which is called a rank or order of a tensor. That means, for example, a scalar which starts with absolute 0 has rank 0. A vector further moves to rank 1, a matrix to rank 2, and so on. We will look into rank and order one by one. There is also something which is called a shape. Now, the shape of a tensor indicates, that means the number of dimensions it has got. So 3 by 3 matrix has shape 3 by 3, 4 by 4, and so on. Don't worry, we are going to explore each of these components in this video. There are certain things which are called components. These are elements and indices which are summed up using Einstein summation convention, etc. We will look into that also. And most importantly, the last and the very central area which makes tensors so important is that transformation rules. That means if I transform from one coordinate to another, there will be a transformation rule ensuring that their physical meaning remains the same regardless of the coordinate system we choose. So from these 1, 2, 3, 4 definitions, I hope it is quite clear that what is a tensor, what are the features. It has got a rank, it has got a shape, it has got various components, and most importantly, when we transfer from a one coordinate system to another, the transformation rules should obey, and it should ensure that the physical meaning is remaining undisturbed. The physical meaning is being measured in a proper way. But these are all English, right? How about showing it on a graphical manner? Let us look into this part of our video. So you see rank 0 tensor looks like this. This is a rank 1 tensor. This is a rank 2 tensor. This is a rank 3 tensor. And rank 4 tensor, I know it is a little bit difficult, but somehow I manage this kind of a pair. So 1, 2, 3, 4. So this is a kind of a rank 4 or rank 5 tensor. Looks like this, and this is the rank 6 tensor. So this is a kind of a, graphical idea, graphical description of what is a rank 4, 5, 6 tensors. That would become much more interesting. And I think by this time you've got a kind of a pictorial understanding of what is the rank of a tensor. We are left with what we called is the shape and size of a tensor, coming up into the next part of our video. So this is a kind of a 3 by 3 tensor. For example, I have denoted by sigma ij. Don't worry about these indices. We will catch up later. Now this part, this the first one, sigma 1, 1. The first one actually keeps track of the plane the component acts on. That means if I take a three-dimensional cube, I need to know the force exactly on which plane, right on the front, on the back, on the left hand side back, where it is acting. And this particular component, say 2, 1, it keeps track of the direction. That means it is left hand side, right hand side, where it is. So from here this definition becomes clear that rank of a tensor is defined as the number of dimension. So 3 dimension, 4 dimension, 5 dimension. In case of string theory we deal with 11 dimensions. So you can just imagine that the number of rank means the number of dimension. And the shape of the tensor represents the size of each dimension. That means each dimension, how much it is, what is the shape and the size. So that clears up the idea of what is a rank, what is a shape, what is a dimension. But yet we are not done with the central part of the idea of tensor, is that what are transformation rules, coming up into the next part of our video. I would take first a Cartesian coordinate, simple x and y axis, and here is a curvilinear coordinate. So I am transforming a data, whatever be the data, from a Cartesian coordinate to a curved space. Now here is the data, this underlined red, whatever, it can be a data, an image, a physics or mathematics data, whatever. But what happens when I transform into this curvilinear, you see it gets stretched. So we have moved from flat space to curved space. Example number 1. Say for example, as I showed earlier, this is a sphere which gets extended to an oblate spheroid. This data get further stretched into this. So what happens is that the object is stretched. Example number 3. What happens if this Cartesian coordinate is being rotated in this direction? So the data in here looks something like this. It gets rotated. So the basic idea is that this coordinate system is rotated. So how do we measure the things? That means how do we measure when things move from this side to this side? It gets into curved space, it gets stretched, it gets rotated, or in some time it gets magnified. And how to keep the measurement invariant in spite of the change of coordinates. We have just found that the very basic definition of tensor, it will follow the transformation rule. However, the laws of physics will be the same. So here it is. The laws of nature should be invariant, and that is what makes tensors so beautiful, that in spite of all those stretching etc., the vectors or the measurements of the data would be recorded, would be recognized, yet there will be a change in terms of coordinate. So here is certain quick, I would say, important points. One is that this is coordinate independent. So tensors would allow physicists, mathematicians to describe any kind of a physical phenomena in a coordinate independent manner. So by this time you would have understood why general relativity is heavily dependent on tensors, because it moves from special relativity to general relativity, from Cartesian coordinate to a curved space-time. Everything changes, yet the fundamental laws of physics should be true. Second thing is that consistency across frame of reference. So in physics, different observers may use different coordinate system to describe the phenomena. Yet the laws of information which are stored in tensors ensure that physical quantities described by tensors would maintain the relationship whatever the ways they are viewed from. Third is that yes, general relativity, the tensor plays a pivotal role which describes gravity as a curvature of space-time. The metric tensor, which is the central part of the general relativity, and it measures the curvature of space-time, and the laws of transformation ensure that this correct tensor correctly describes how coordinate or gravity affects objects in all coordinate system. Three quick points which essentially tells you that what is the basic idea that rules the tensors and why tensors are important. Now when we say that coordinates are moving from one place to another, what do I actually mean by that? Can we show it in a much more easier graphical manner? Coming up into the next part of our video. So let us take that this person is throwing a ball in one coordinate system over here, and the same person is throwing a ball in another coordinate system, and this coordinate system is rotated. It is not the same, it is rotated. So what do I mean by that is that events will be measured in the same way in all frames of reference, whether it is rotated, stretched, or it is magnified. Same another example, the person is throwing the ball over here, and in this case the frame of reference is much more magnified. That is, the x and y axis is extended, yet the laws of reference will be the same. Again, the events will be measured in the same way, and that brings us to the famous line. This is the same. The sphere, this line would get extended into this line. So whatever happened, whether it is rotated, stretched, or extended, the laws of nature would be the same. And that gives us to Einstein's famous quotation is this one. The general laws of nature must be expressed by identical equations relative to all other systems, whichever way they are moving. So that was the central idea of general relativity, and that actually brought Einstein to develop tensors, and that is why tensors actually helps us to measure the laws of physics irrespective of whatever happens to the coordinate system. So this next description shows even better that space and time, once it is unified into space-time, this person is throwing, so the event would be the same in case of a stretched coordinate system or when it is unified into a space-time. So universal laws of physics should not depend on any particular coordinate system, and here we need something which is called a metric tensor, which we will eventually look into this series of video. It describes how distances are measured, and when the coordinate system changes, yet we can measure the distances. So this is what we know, what we call are basically the transformation rules, and that is how tensors helps us to identify things. So here is a clearer diagram. I showed it earlier that tensors actually generalize the concepts of vectors, and tensors extend the concept to any number of dimension. Here it is 0, 1, 2, and so on. So if I get a kind of a flat space, when I extended it into this kind of a curvilinear time and space, what we get is this. The curvature of space-time is described by the metric tensor, which is a rank 2 tensor, and the metric tensor tells us how distances and angles, I mean to say from flat space when we move into curved space, how they changes, and it also tells how objects moves in space-time as described by the geodesic equations. We will come to those technical words, what we mean by metric tensor and geodesic in due course of time, but this is what completes our discussion about the transformation rules of tensor. But the most important thing is that tensors were actually not used to study originally to measure the curvature of space-time and some or the distances. It is neither used to carry a stretched coordinate system or a space-time manifold. It is used to describe something else, something very different. What is that? Let us look into the next part of our video. We will look into the history soon, but before that I would like to show you tensors were actually discovered, I would say they were reinvented when we studied the usage and the study of crystals. Now you see on the left hand side I have shown some of the crystals, and you can very well see that these are actually different types of shapes, different kind of directions, and it takes multiple faces, etc. So when I plot a kind of a crystal over here, you see it takes a simple shape, then it gets a rhombohedral, then it gets a body center. So a crystal, when I plot it into an XY or a kind of a coordinate system, it is not that simple. It is not that simple that I will just mention a vector which has got a magnitude and direction, but it has got numerous faces. Again, if I plot, I get over something like this: a hexagonal, a triclinic, and lot of tetragonal faces. So what do I mean by this is that there are many faces and many directions which actually vectors would not be able to measure them. So as you see that crystals come in different shapes, different directions, different sizes, different kinds of magnitude and shapes, we need tensors, because this is important. It is not only important about the direction, but also on which plane it is occurring. We will soon see the person who was actually studying crystals, and for the first time he invented, or I would say redefined the concept of tensors. It was from this concept of crystals. But the concept is that we have seen that it has got many faces and directions, and vectors are not being able to define. But what exactly is the underpinning factor which actually resulted in the discovery of tensors? What was not being defined in vectors? Let us look into the next part of our video. So if I take a crystal and if I try to heat it, you will see that it will expand by the same amount in each direction. So here is a crystal, and if, for example, if I take a glass, and if I heat it, it will expand by the same amount in each direction. But when I start heating a crystal, what happens is that the expansion of crystal will differ depending whether one is measuring in the A axis or in the B axis. So what happens is that elasticity and thermal expansivity cannot be expressed in terms of scalars. So when it heats, when the crystals generally heats up, the expansion happens in different direction. It takes different phases, and that is why we need tensors. So we use tensors as a tool to deal with more complex situation, because study of crystals are central and important, because understanding the bulk behavior of rocks can actually wind up lot into mineral physics. So this was the basic idea, the basic reason that crystals were not being studied by scalars or vectors, because the thermal expansivity cannot be expressed in scalars, and we need something different, and that is why we need tensors. Now the question is that we all understood that it stores information, it helps in coordinate transformation, it also helps in studying crystals. But the main area of concern is that why should we study tensors? Is it that studying the tensors is absolutely useful? Is it that mathematics or physics or our graduation or postgrad cannot go without the study of tensors? Let us look into the next part of our video. We will examine the real meaning and why should we study tensors, and you will be surprised to see that tensors are so important that it is embracing all parts of our life. First, we will start with differential geometry, which is an important aspect. Tensors are used to describe curvatures. It is an absolutely essential part in differential geometry. If you talk of linear algebra, which is taken up in our college days, tensors are very important, because a linear transformation won't be understood until and unless we understand linear algebra. Obviously, general theory of relativity. I have spoken in numerous videos about the usage of tensors, and in my upcoming webinar, which is happening on 30th of September, you can participate, and I will tell you how tensors are important in the study of general theory of relativity. Well, quantum mechanics, again, it is important because tensors are used in quantum mechanics in order to represent vectors, operators, and observables. So right now you can see almost three areas: differential geometry, linear algebra, quantum mechanics. These are essentials part of any kind of a BSc or MSc study, so you cannot just ignore tensors. Also, computer vision, because tensors are used to store lot of images, and images are so huge nowadays of these HD and other cameras that normal data is unable to store, so we need to use tensors. Electromagnetism, yes, Maxwell's equations and Faraday's law are later being expanded, and they are used in denoting tensors in a much more smarter and easy way. Fluid mechanics, very important. Those who are studying fluid mechanics must know that tensors are used in fluid mechanics because it presents stress, strain, etc. And lastly, what I showed right now, I don't need to mention it again, crystallography and material sign. Tensors are employed because crystals, as we show, that the thermal expansivity cannot be denoted by scalars. So piezoelectric tensors, which describe the response of materials, are very much used. So that is why you see that tensors are embracing us in every sphere of your study. But now you might ask a question that these are all related to physics, mathematics, fluid mechanics, etc. But is it that tensors are used outside physics and mathematics domain? What are those? Are they at all used in other areas of our world? Let us look into the next part of our video. Are tensors used other than physics and mathematics? Well, the answer is obviously a quite yes. First, data representation. Tensors actually provide a versatile way to represent any kind of a data. It can be higher dimensions such as images, videos, sensor data. It can be anything. So the representing of the data nowadays are being done by tensors. The second thing is that deep learning and neural network, because there's a huge amount of data, tensors are central to deep learning, neural network, layers, activation. It's huge because it comprises of a huge number of data handling. Numerical computation, yes, tensors are used for GPUs and TPUs. These devices are actually optimized for tensor operations, making deep learning and scientific learning much more useful. We also see that higher order derivatives that we use in machine learning and optimizing algorithms, tensors are actually used for computation of higher order derivatives. We also already have seen that nowadays with the coming of this HD and the DSLR cameras, huge amount of data is being captured, especially in the form of image. And how can we keep those images? These are used in tensors. So an image convolution operations in order to apply filters and extract this data is being done by tensors. Data analysis, data mining, yes, a lot of devices, multimodal data are used and data analysis, data mining is being used. And lastly, climate modeling, which actually you understand climate means a huge amount of data to be stored. How can we store them in order to predict complex climate patterns, etc.? The usage of tensors are almost inevitable. So from there we come to a conclusion that in summary, tensors are important because in one way they provide a unified and efficient way to represent and manipulate huge amount of multidimensional data, which enables in a wide range of fields starting from AI to deep learning, physics, engineering and scientific research. So this gives you an idea that it is not only physics and mathematics but a wide range of business domain actually are using tensors. So far so good. But who actually discovered tensor? What is the origin and how do tensor actually came into our world? Let us look into the next part of our video. In this part of the video, we will actually explore the origin and the history of tensors. Well, first of all, it actually started with Augustin Louis Cauchy, and we all know about what is called the Cauchy stress tensor. It was further expanded by William Rowan Hamilton, 1846, the tensor of the quaternion, and we will originally see in a few minutes from now that how William Rowan Hamilton was the first person to coin the term tensor. Then comes Bernhard Riemann, a huge amount of contribution in terms of Riemann curvature tensor, etc., which plays a pivotal role in general theory of relativity. Then we come to Josiah Willard Gibbs, who was actually dealing with crystals, and it was called dyadics and polyadics, which was later termed as tensors. Then we come to Dr. Waldemar Voigt, who was actually doing researches on crystals, and in order to mention the stress and strain of crystals, he came to know about tensors. And finally, Gregorio Ricci Curbastro discovered the famous Ricci tensor, and his student Tullio Levi Civita, who was a pioneer of discovering tensor calculus. Well, the history is huge, enormous, but it is out of the scope of our video, so I won't go further, but these are the eminent and prominent names of people who actually worked upon tensor and brought the tensor calculus in front of us. Well, as I was talking about this famous Irish mathematician, Sir William Rowan Hamilton, and this is the name of the book, On Quaternions or a New System of Imaginaries in Algebra, 1846. 1846, where he actually coined the term tensor. And here you see I have underlined that which we may call tensor for the quaternion, and the tensor is what we call this is this. So this is the very paper in 1846 when William Rowan Hamilton actually coined the term tensor. Now we also come to this wonderful gentleman, Dr. Voldemort, and this German paper, Die Fundamental, and anyway, the meaning in English is the fundamental physical properties of crystals in elementary representation. It's a German paper. However, I have underlined after translating it into English that these are the lines where he actually founded and coined the term tensor. Tensoren, tensorstripel, tensor. So this is the original paper in German, but this is where he coined the term tensor. So Dr. Voldemort contribution is something which is unforgettable, which is he did a pioneering research in terms of crystal in elementary represent. This is the original paper in German, and these are the areas where he coined the terms tensor. Now there is a myth which I often find when I talk to my students or otherwise, that Einstein actually discovered tensors. Einstein actually founded tensor, and it was only Einstein who discovered tensor calculus, and I want to break the myth. Here is a question: did Einstein discover tensor calculus? Now I would answer the question whether it is yes or no into the next part of the video. But before we go ahead and answer whether Einstein actually discovered calculus or not, we will have to encounter an unknown German physicist which you might not have heard the name. On the left hand side you see him. His name is Marcel Grossman. Well, Grossman was actually, the parents were Jules Grossman and his mother Katharina Honorate Lichtenhan. 1893, when Marcel was 15 years old, his family moved to Switzerland and settled in Basel. After completing his high school in Basel, Grossman entered what is called the ETH, the famous public university in Switzerland, and he was aiming to study mathematics and become a teacher of gymnasium in mathematics. And during this time he got in close associate with Mileva Maric, Einstein's wife, and Albert Einstein himself. Grossman's father actually helped Einstein to get his job at the Swiss Patent Office in Bern, Switzerland, and it was Grossman who helped to conduct the negotiations to bring Einstein back from Prague as a professor of physics and get a job at the Zurich Polytechnic. I would answer the question. Have you already got a hint why I am speaking of Marcel Grossman? So here you see that this was the time when these three people, Grossman, Einstein, Michel Besseau, and Mileva Maric, they were all working, and they were a student at the ETH Polytechnic, spending their golden days. And here I have underlined that Grossman was actually an expert in differential geometry and tensor calculus, and it was just the mathematical tool which Einstein required in order to frame his theory of gravity. So I just wanted to give you a hint that it was not Einstein. Rather, history says that Einstein never knew anything about differential geometry and tensor calculus, and it was Michel Besseau, his Italian famous friend, and particularly Marcel Grossman, who was an expert in differential geometry and tensor calculus, actually introduced Einstein what is called tensors. Before that, Einstein hardly had any idea. Now you might say, are these words, or can we show certain evidences? Certainly we can show certain evidences. But before that, I would like to show you that what happened during that time. So Einstein actually left Prague on 25th of July 1912 and registered his name into this residence, which is called Einstein House, or the House of Einsteins. With a family of 4, his sons being 8 and 2 years of age, it must have taken a few days to settle in, and the Grossman family may have been helping the Einstein family to settle here. But Marcel Grossman himself was busy preparing of a lecture at the 5th International Conference of Mathematicians, which was held in Cambridge from 22nd of August 1912. Now we know, however, that soon after arriving here in Zurich, Einstein and Grossman started a collaboration, and this was which led to the famous discovery of general theory of relativity, and that would in any case result in Grossman's most well-known scholarly achievements. If we know that what Einstein told is this: he told Grossman, you have to help me or else I will go crazy. So these words actually tells that Einstein was feeling helpless in order to find a covariant theory of gravity. The loss and the I would say the knowledge of tensors was not quite clear to him. And now the letter on October 29th to this person tells that I am now working exclusively on that gravitation. Arnold Sommerfeld, he writes that I am not working on that on the gravitation problem, and believe that I can overcome all difficulties with the help of a mathematical friend of mine here. Who was that mathematical friend? Marcel Grossman. I have underlined in red. But one thing is certain, never before in my life I have troubled myself over anything so much, and I have gained enormous respect for mathematics, whose more subtle parts I consider until now in my ignorance as pure luxury. This book of Abraham Pace, which is called Subtle is the Lord, expresses Einstein's further dilemma in finding tensor calculus. This problem remains insoluble to me until 1912, when I suddenly realized that Gauss's theory of surfaces holds the key for unlocking this mystery. From him, that means to Grossman, I learned the first time about Ricci and later about Riemann. It's time to show you some manuscripts right on your screen. You can see this is the top portion of the Zurich notebook. And it also showed Einstein a way to extract a reduced quantity from the Riemann tensor that transform as a tensor under unimodular coordinate transformation. Although given up the time, this particular tensor appeared 3 years later as a candidate gravitational tensor in the first part of Einstein's famous 4 memoirs of November 1915, which marked the breakthrough to the final theory of general relativity. Further, you see, this is actually what is, and this underlines, this page shows actually that Grossman introduced Einstein to the Riemann tensor as a mathematical resource, and finally framing its general theory of relativity. I have just written a little bit on this partial differential part so that these things are much more clear. And here you can see I have underlined in red, this is actually what is called Grossman tensor of the 4th manifold. So that actually completes our today's video, an overview, history and understanding and breaking the myth that it was Marcel Grossman and Michel Bessot and Minerva Maric who were masters of differential geometry, introduced differential geometry and tensor calculus to Albert Einstein, which helped him to form the general theory of relativity. Here is a quick summary of what we have learned. Yes, we have learned about what is a tensor. We learned what is a tensor, what makes tensor very unique. We learned certain important features like rank, order, shape of a tensor. What are the transformation rules? And we have seen graphically what does it mean by transformation rules. Study of crystals, why we should study tensor, and was it Einstein who discovered tensors, and we saw in details what about is the origin and history of tensors. So in the next part of the video, we would start now with the real mathematics. Coming up next would be the coordinate transformations. I would be explaining on covariant and contravariant vector components and how the basis of the vector transformation actually shows the central idea of coordinate transformation in tensors. That's all for today's video. I think you have liked it, and I'm immensely thankful for you for watching this video. If you like this video, hit on the subscribe button and click on the bell icon to get all the notification from Physics for Students. This is my email ID and this is my other channel on general theory of relativity, and you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Please do let me know how do you like about this video and put up your comments, and do not forget to subscribe to this channel, because Physics for Students will be soon back with more videos, and this tensor playlist has just started, so we will now start dealing with the real mathematics of tensor calculus. This was just to give you a motivation and an overall idea and a fascinating history of tensor calculus. More are still waiting. Thank you very much for watching this video.